What's up, kiddos? Today we are going to finish our foldable notes that we started yesterday in class. So I believe that we got through Dalton and our buddy JJ Thompson. But a quick review, make sure you have your foldable notes out. Dalton, Thompson, Rutherford, Bohr, and lastly, you got your cloud model. And then again, we're going to use those flaps, lift them up to record our notes today. So, a quick review, we talked about Democritus, the Greek guy that had the first idea that matter was made up of atoms, and we give him credit for the word atom, which really means indivisible or uncut. Now, we didn't write anything down about him, but I want you to remember that Democritus was the guy that first said all matter is made of atoms, and that he gave us the name atom. Our buddy John Dalton, he was the school teacher that basically had the first atomic theory. And yesterday, you included these in your foldable notes, his atomic theory, all the different aspects of that theory, much of the ones we still use today. And I also wanted you to add yesterday in Dalton's, in the notes for Dalton, that he believed that the atom looked like a sphere. So if you did not yesterday, make sure you draw a circle or a sphere to represent that was what his model of the atom looked like. But he was the first guy that really had evidence and said, he had the first atomic theory that we still use a lot of from today. We also talked about J.J. Thomson. He had the cathode ray tube experiment where he took a cathode ray tube, ran a current through that, and used a magnet, and it was able to see that, hey, that green light that he saw was actually a particle. It was not just light. And what he discovered the electron. So if you forgot to put that in yesterday, J.J. Thomson, cathode ray tube, he discovered the electron, and there's a picture of his model. Make sure you include that. He thought that it was a round sphere, round positive sphere, but there were little tiny electrons inside there. And we call that the plum pudding model, but I told you guys I like chocolate chip cookies better. So very, very similar, where your chocolate chips are the negative electrons sitting in that positive sphere. So we're picking up today with a guy named Rutherford. Rutherford, or Lord Ernest Rutherford, he is famous for something called the gold foil experiment. He was shooting a radiation gun or a alpha particle gun at a small, thin layer of gold foil. Like, what does that even mean? Well, an alpha gun is small, tiny little, you can't see them, it's radiation, very powerful radiation, alpha particles. And he expected to shoot this little radiation gun through this gold foil, and you would expect him to go right through. It would be similar to, hey, you have a wedding cake or a big cake, and there's bullets shot at the cake. You would expect the bullets to go straight through the cake, or straight through the gold foil in this case. But here's what he expected up top here. Hey, there's the alpha particle source shooting the particles. There's your little gold foil and this little detector screen to let you know where those particles hit. Because again, we're talking about radiation, we can't see it. So he expected this. He expected him to go right through. But what he got was something like this. Now, the majority of those went straight through, but some kind of deflected off at different angles, and some even almost bounced right back. So imagine shooting, bullets being shot at a cake and bouncing back at you. So obviously he was incredibly surprised. Something had to be going on. He obviously had discovered something. Here's one more picture, kind of what it would look like. Here's his alpha particle gun that he shot, these little beam of radiation. Most particles did go straight through, but some were bouncing off at different angles every so often. And it kind of looks like, here's a picture of it, kind of a cartoon picture. The particles are being shot, but most go through, but every once in a while, some are bouncing back. And he wasn't sure why that was happening or what was going on. So what he proved, or what he thought he discovered was, hey, the atom was mostly empty space because most particles went straight through. Also, every once in a while, some of those particles would bounce backward. Now, I didn't tell you these alpha particles are positively charged. And so if you shoot particles at something that also has the same charge, like charges repel. So what he discovered was in the very center of the atom, there was a very small a very dense, positively charged nucleus. And it's positive because the alpha particles he was shooting were deflecting back because like charges repel. So it's almost like if we had Lucas Oil Stadium, like our video last week, Lucas Oil Stadium, and at the center of Lucas Oil Stadium was a marble or the size of a pea. That would be the size of the nucleus that he was discovering. So Lucas Oil Stadium blown up to a sphere, at the very center 50-yard line would be your nucleus, tiny marble or the size of a pea. And so if we're kind of thinking of analogies here, think of a peach. Now, not the best, but a peach has a pit, like a nucleus in the center. So here's what I want you to write down. I want you to draw for Rutherford. Make sure you include the gold foil experiment. He proved the atom was mostly empty space because most of his particles went straight through. But some of those particles bounced back, those positive alpha particles. So he discovered that there was a very small, very dense, positively charged nucleus inside the atom. So here's what I want you to draw for your picture of your model for Rutherford. Again, a small positive nucleus with those electrons kind of around the nucleus. Some other important discoveries we're not going to spend too much time on. Two different gentlemen were given credit with discovering the proton and also the neutron. Goldstein in 1886, the proton, a positive charge, and Chadwick in 1932 discovered the neutron, also in the nucleus as well. But we're not going to spend much time. Give you a heads up that those two particles were discovered. We're going to move on to our next model. This model is called the Bohr model, Niels Bohr. And so the model looks pretty simple, but if you notice, you got your positively charged nucleus in the center, and you also have these electrons, and they're definitely in fixed orbits. They're in specific orbits, almost like the nucleus is the sun, and the electrons are the planets orbiting the sun. So this model is a little bit different from Rutherford's because in this model, and here's what I want you to write down. So put this in your notes right here. Bohr's model, he said electrons move in specific orbits. Just like planets move around the sun in specific orbits, we sometimes call this the planetary model. So it's similar to our solar system. And we still use these models, and we'll draw these models in class for you later on. But this is the Bohr model. Basically says electrons stay in their own specific orbit, just like planets orbit the sun. Electrons kind of orbit the nucleus of our atom. So electrons have their own specific orbit, and they are stuck in those orbits. Our last model, our current model, is called the quantum mechanical model. We're going to call it the cloud model. I mean, quantum mechanical, kind of a mouthful. We'll call it the cloud model. And you're looking down here like, what are these balloons, Mr. Grimm's, orbitals? What does that mean? Well, in this model, we're going to build off the Bohr model. So the Bohr model said electrons stay in their own specific orbit. That's not what happens here in this cloud model. Electrons can actually move in and out of other orbits. So we have an idea where electrons are. We have an idea of their shape and pattern. They're moving around. However, we don't know exactly where an electron is at any one time. So they're moving so fast in and out of their orbits, it's almost like there's a cloud of electrons around the nucleus. Now, I'm not going to go too in depth with this quantum mechanical model, but this cloud model is based on like probability. You know, we can have an idea where electrons are, but we don't really know for sure. We just kind of have a mathematical idea of, hey, electron could be here any one time based on that principle. So what does that mean for us? Here's what I have you guys write down for the cloud model. The cloud model basically says electrons move rapidly in many different locations around the nucleus. Now, what's different from the Bohr model to this model? Well, the cloud model, our current model, says electrons can move in and out of their orbits. They are not stuck or fixed in their one orbit like the Bohr model. Now, these orbits or areas, are called clouds, and they have specific shapes. But it's really impossible to know the exact position of electrons in these clouds because they're moving so fast in and out of that area. So quantum mechanics, we have a probability of knowing where the electrons are, but we can't say for sure where they are at any one time. So it's like there's this giant cloud of electrons around our nucleus, around our protons and neutrons. So to draw this model, I'm going to draw some protons and neutrons in the center, and then kind of have a shaded area or a cloud of electrons moving around to show, hey, they're not at any one exact position. They can move in and out of orbits based on how much energy they have. So kiddos, that is the last thing I want you to add to your notes today. Make sure you have everything from Dalton all the way to the cloud model.